talk about. Okay, so curve sketching or graphing using calculus techniques. The basics, what I think of as the basics anyway, of calculus techniques for curve sketching are going to include first derivative, using the fact that the first derivative gives us the slope. Ooh, I might need to switch to my other pen. This one's a little bit harder to write with. Let's see here. Okay, so if we have a function f and we look at its derivative, it tells us the slope, right? And in particular, if that slope is positive, then what does that tell us about the original function f in terms of its graph? It tells us that its graph, if you read it from left to right, is going upward or increasing. Okay, and if f prime, the slope of the function, is negative, then it tells you it's decreasing. It's going downward. All right, so this gives us a bit of an idea of the shape of a graph, where it's going up and where it's going down. But it's possible for a graph that's going upward or increasing to be going upward in this manner, or it could be going upward in this manner. The first one we call concave up. Looks like it could hold water. And the second one we call concave down. And you can have, and actually this one, oops. You can have a graph that's increasing and concave up, or increasing but concave down. And then similarly, if a graph is decreasing, you can still have it be either concave up and decreasing, looking like a kind of the concavity is that if you were to imagine drawing tangent lines, if it's concave up, it's getting steeper, meaning the slope is getting bigger. So this is going to happen when the derivative has itself a positive slope, or in other words, when the second derivative is positive, then you're going to have a concave up scenario. And when the second derivative is negative, then the slope of the tangent lines is decreasing. So the slope of the first derivative, the second derivative is the slope of the first derivative, and it's going to be negative. So in order to analyze the shape of a graph and get a nice idea of the curvature, you only need to know about the first and second derivatives. Now, the first derivative and the second derivative, if you're analyzing them, they're going to change from positive to negative in one of two situations. When the first derivative or second derivative, whichever one you're analyzing, is zero, or when it's undefined. So when we analyze the function, we're going to set up sign charts and for both the first and second derivative and find where they're equal to zero or undefined. So let's look at an example. So say that I wanted you to graph y equals, let's see, let's do x to the fourth minus 4x cubed plus 16x. And we're going to use the first and second derivatives to do it. We're going to include any intercepts that we can find. We're going to include any relative extrema, meaning where the graph changes from increasing to decreasing. Points of inflection, meaning where it changes from concave up to concave down. I really do think I need my other pen. Hold on a second. See if this pen does better here. And we have asymptotes. That's not going to apply here because we have a polynomial function, but normally we would include asymptotes as well. All right, and let me not call it y, let me call it when y is 0. Your y-intercepts when x is 0. So let's find the y-intercept first. So that's just f of 0. So for our x-intercepts, we're going to let y equal 0. We're going to get 0 equals x to the fourth minus 4x cubed plus 16. So we want to try and factor this guy out. So we're going to have x times, we're going to have x cubed minus 4x squared plus 16. All right, and we already knew that x equals 0 was going to be an intercept, and now what that leaves behind is x cubed minus 4x squared plus 16, which is not so easy to solve. I don't want you to spend too much time on trying to solve equations like this one. If it's not effective, if it's not efficient and effective, then just go on to other tools. Okay, so we know one of the x-intercepts. All right, let's see what else is happening here. This from increasing to decreasing, or potentially changes when the first derivative is equal to 0. So, oops. Let's look at the original function was f of x equals x to the fourth minus 4x cubed plus 16x. So taking the first derivative, we have 4x cubed minus 4x squared. I'm sorry, not 4x squared. Minus 12x squared, bringing the power up front and subtracting 1 from it. And then, ooh, this is not such a great problem for me to be working right now. Plus 16. I really wanted one that would work out nicer. What can I do? Let's see. Hold on a second. Sorry, I'm still here. I'm just trying to determine if I want to continue with this problem or give you a little slightly cleaner one. Just a sec. I want to see how messy it's going to get. Okay, it's not too bad, so we'll keep going. All right, so f prime of x is equal to 4x cubed minus 12x squared plus 16. So this is what we're trying to figure out then, is where this derivative is positive or negative by starting with where it's equal to 0. It's never going to 4. Okay, so I'm hoping that this has some linear factors, and so in other words, something like x minus 2 or x plus 4. And based on that it has to end in a 4, I'm thinking that should be 0 if we plug 1 in. How about negative 1? Okay, so if x minus 1 were a factor of this guy, then that would mean that if we plugged 1 in, we would get 0, right? But if I'm noticing here that if I plug 1 in, I get something other than 0. So it must not be x minus 1. Let's try x plus 1. Okay, if x plus 1 is a factor, then that would mean that if I plug negative 1 in, I'm looking to see if x plus 1 is a factor. If I plug negative 1 in, I should get 0. So that would be this guy, x cubed negative 4x times negative 4x times x plus 1 is negative 4x squared minus 4x. And subtracting, we get positive 4x, bring down the 4. So x plus 1 goes into that 4 times evenly. All right, so what we see here is that factors pretty easily into x minus 2 quantity squared. Okay, so setting each factor to 0, then we're going to have x equals negative 1 or x equals positive 2. These, and as we analyze this, use the factored form of this first derivative. Essentially, the first derivative was, let's see, we took out a 4 times x plus 1 times x minus 2. Negative 1 to 2, 0 is a good test value. So plugging in 0 would give us positive. Oh, you know what? I made a mistake because that wasn't just x minus 2. That was x minus 2. So that should have been positive, negative, positive, which would have been a negative. Sorry about that. Come on, eraser. There we go. All right. And then this one is going to be plugging in 0. We're going to positive. So this is going to be positive. And then plugging in a 3, we'll also get positive, positive, positive. Okay, so what we see is that the first derivative is telling us that function f is decreasing on the interval from negative infinity to negative 1. And then it's increasing me scoot this up a bit here. F is increasing. F prime of x was 4x squared minus squared plus 16. 4x squared minus 12 minus 24x plus 0. Okay, so our second derivative can change from positive to negative when it goes through 0 as well. So we want to find the values that make 12x squared minus 24x equals 0. Okay, so factoring out of 12x, again, we might as well use the factored form of the second derivative to analyze it. It makes it easier to check the signs. So the second derivative, okay, when x is -1, we would get negative times a negative, which is a positive. And 3 or 5 or whatever, if you plug that in, that's going to give you positives. Positive times positive is positive. Okay, so now we know that our original function f is concave up on the interval from -infinity to 0 and the interval from 2 to infinity. And we know that its f is going to be concave down on the interval from 0 to 2. Okay, so now it's going to be important to know the value of f at the points where the shape is changing. So what I mean by that is we know that it changes from decreasing to increasing at -1, and also we know that the concavity changes at 0 and 2. So we're going to want to know the values of f at 0, -1, and 2, so we can plot those points and then fill in the shape of the graph in between. So back to our original function. Let me write it down again. So our original function f was f of x equals x to the 4th minus 4x cubed plus 16x. So we're going to just plug into that function. If we plug in 0, we get 0. We already knew that. If we plug in -1, we're going to get +1 plus 4 minus 16, so -11. If we plug in 2, we're going to get 16, let's see, minus 4 times 8, so minus 32, plus 32, so we're going to get 16. Okay, so these points, 0, 0, -1, -11, and 2, 16, are going to be like our framework. Okay, and I'm going to draw a graph. Obviously that's 0, 0. I'm not gonna, oh no, come back, come back. Okay. All right, so we have 0, 0 here, and then we're gonna plot -1, -11. It's being very glitchy today, sorry about that. So okay, and then 2, 16. K2, 16. All right, and now we need to fill in the gaps in between. So first of all, we know since the original function has an even degree that it's going to go either up on both ends or down on both ends, kind of like a parabola, an x squared function, right? But and since the coefficient is positive, it's going to go up on both ends. So what we expect to see is that it would be going up here and up here. Now, is that consistent with what we found when we analyzed the first derivative? Let's see, when we analyzed the first derivative, we said it was decreasing to -1, so yeah, that would be consistent. And it's increasing after 2, so yeah, that would be consistent. Focus in on the concavity. So according to our second derivative sign chart, it was concave up from -infinity to 0. So that means that we expect it to be concave up after 2. All right, so I'm going to zoom in because it's going to be hard to draw the concavity unless we zoom in a bit. Let's see. Maybe open this guy up here. Oh, let me erase that. Okay. Okay. All right, so starting with the bottom half graph, and this goes on forever. All right, and so we were asked to give any relative extrema. That's where the function changes from increasing to decreasing or vice versa. So this would be a relative minimum. And we were asked to label, there's no other place where it changes from increasing to decreasing. We were also asked to label any relative, any inflection points, which is where it changes from concave down to concave. Hold on just a minute. I think I'm overworking my computer. Okay. Oh. Okay, so this is a nice website for graphing. Okay, oh, got a bunch of notifications here. Okay, so we're going to graph the function y equals, and we have x to the fourth, and we're going to do minus 4x cubed, and then plus 16x. Okay, and I'm going to zoom out a bit. There we go. And I think I'm going to adjust my horizontal scale as well. Spread it out. Okay, so that gives you a little bit better idea of the shape than what I could draw. But you see how it's concave up until 0, and then it's concave down until 2, and then concave up again. And the important points that we labeled, let's see, there was 216. Come on. You just type it over here. Okay, there's the point 216. And let's see, we also we're interested in 0, 0. And we also were interested in -1, -11. Okay. All right, so that was a polynomial function. I'll go ahead and graph a rational function because those involve asymptotes and they can get a little bit more complicated. Zoom out here. Okay, if there's a particular exercise you'd like me to work, just let me know. Okay, so the items that we want to include to label the denominator, then potentially we do actually have asymptotes this time. So first let's talk about intercepts. So remember, the intercepts are where the x or y are 0. So to find the y, 0, but x squared plus 1 equals 0 doesn't have any real solution. So we're not going to have any x-intercepts. Let's see. Relative extrema. Well, actually, let's go to asymptotes first, and then we'll analyze our first and second derivative to find the relative extrema and points of inflection. So asymptotes. So vertical asymptotes of a rational function, a function that's a fraction, are going to whenever the denominator is 0 and the factor that causes it to be 0 is not all. What that would indicate is that you have a hole in the graph at -2 rather than a vertical. And so that's the limit of x. So in general, when you have a rational function, the coefficients of the highest degree, if you have the same degree in the numerator and denominator, the coefficients, the ratio of the coefficients is your horizontal asymptote. So we have a horizontal asymptote y equals 1. It would work out the same if x was going to negative. First derivative we're going to find using the quotient rule. Then the x squareds are going to cancel out. We're going to have -5 times 2 is -10. So -10x over x squared minus 4 squared. Okay, so that's our first derivative. We want to know where it's equal to 0 or undefined, because that's potentially where we have a change from positive to negative for the first derivative. So that would mean the function changes from increasing to decreasing at that value. All right, so in the case of a rational function, we find where it equals 0 by setting the numerator equal to 0. So we want to know where negative 10x equals 0, which is when x is 0. And we have an undefined function. Okay, this is our first derivative sign chart. Make sure to label it so you don't forget what it is. And I'm going to go ahead and write what the first derivative is equal to here. It's already in a nice factored form, so that's good. So example, numerator positive again, and the denominator's up, and 0 to 2. Okay. Let's go ahead and figure out the value of f at these important points. We know that at negative 2 and 2, the function f is undefined. Okay, and now we're going to focus in on our second derivative and our concavity. So if our first derivative was negative 10x over x squared minus 4 quantity squared, then let's go ahead and use our quotient rule again to get our times the derivative of the bottom, which is a power rule, chain rule problem, right? So this is going to be 2 times x squared minus 4, x squared minus 4. And this is all over x squared minus 4 squared squared, or to the 4th power, but we'll get there. Okay, so we definitely have an x squared minus 4 in common. Let's pull that out, x squared minus 4. And we have a 10 in common. And it's up to you if you want to pull out a negative 10 or positive 10. I think I'm going to go ahead and pull out a negative. This is going to change to change sign to a negative. Okay, sorry guys. Kind of lost you there. Hopefully we're back up and running. Okay, so we were finding the second derivative and we were at the point... Oh boy. And we had x squared minus 4, and then we had what was left behind inside, x squared minus 4x squared. And in the denominator, we had x squared minus 4 quantity to the 4th power. And right away, we know where it's going to be undefined. So in order for the second derivative to equal 0, we would need the numerator to equal 0, which would mean that negative 3x squared minus 4... I keep losing you. Negative 3x squared minus 4. If that were 0, then the numerator would be 0, causing the second derivative to be 0. So this would mean that we would have negative 3x squared equals positive 4, which would mean x squared is negative 4/3, which can't happen. And then, I'm not sure if we're working. Okay. All right. So, I mean, it can happen, but not in with a real solution, right? So, if x squared minus 4 equals 0, the second derivative is undefined. That happens at plus or minus 2, which makes sense because we know we have asymptotes there, right? I say of course because there's vertical asymptotes there, so it makes sense. All right, and so now we're going to make the sign chart for the second derivative. Let me actually go up a bit. Okay, well, the numerator here is always going to be positive, right? And in the denominator, negative 3 gives us 9 minus 4, which is a positive, cubed is positive. The function itself will be concave up, negative infinity to negative 2 and 2 to infinity. And concave down from negative 2 to 2. Okay, so we have found the concavity. I know that the stream is going in and out, and I do apologize for that. And there's no new point that we've found where the concavity changes that we didn't already consider important, because where the concavity changes is exactly at your vertical asymptotes. So what we're going to do is we're going to plot that one important point, the Y-intercept, which also happens to be where the something else happened there. What was it? Oh yeah, so there was a change in increasing or decreasing at that point. And then we're also going to plot our asymptotes, and we'll use, so we'll make this 1, 2, 3, okay, and so we had our y-intercept 0, negative 1/4 would be right here, 1/4. And we x-axis into 3 chunks, you can see there, and the one in the middle we have a point for, and it's an important point. It's where the graph changes from increasing to decreasing, but we don't have any values to the left or to the right to know which portion of the plane that we're in. So it's a good idea to plug in a value or two and see where we are. So equals x squared plus 1 over 9 minus 4. That's going to be 10 over 5, which is 2. So let's plot the point 3, 2, just so we have a frame of reference for where we're located here. And then maybe on the other side do negative 3. G of negative 3, let's see what that one is. That's also going to be 9 plus 1 over 9 minus 4 equals 2. So that's a nice point. That worked out nicely. All right, so negative 3, 2. Okay, and now let's recall what we know about the shape of the graph. So coming back up here, remember f is increasing between negative 2 and 0 and from 2 to infinity. So between negative 2 and 0, f is increasing. It also happens to be concave down between negative 2 and 0, right? Between negative 2 and that point and 2, between 0 and 2, still concave down, but decreasing, right? Then after 2, so 2 to infinity, we have concave up, right? Which makes sense if you look at where we're drawing. Oh. Now this is freezing up on me. Computer's not happy today. So we have concave up. All right, so I'm sorry that the stream has been so bad, but let's just really quickly identify. We don't